All right, what's up, everybody? My name's Mr. Hooker. I know most of you, but I don't know all of you. So if I don't know you, hello. If you're watching this, we already kind of got to meet on our C Day, first day Zoom meeting. Um, Hopefully, you are watching this prior to the start of our first official B Day, which is on Friday. So hopefully, you're watching this on Wednesday or Thursday. This video is going to be a bit longer than most of the videos will be in the future, primarily because I'm going to be stopping to explain some certain things that I'll only have to explain once, and partially just because I got a lot to talk about. So, I am recording these videos on my desktop computer. As you can see, I'm in my room at my house, so it is what it is. We're doing the best we can here with the virus and everything. And I've also got a fancy little setup here so I can transition between the full webcam and my slides. Okay, so I'm going to do my best to kind of go back and forth between those, mostly on the slides, just to kind of give it the real sort of in-class feeling. Okay, so without any further ado, let's go ahead and dive in. Okay, so this is for Unit 1, Topic 1 of the AP Chemistry curriculum. Unit 1 is on atomic structure and properties, and Topic 1, what we're going to be talking about today, is on moles and molar mass. And we're actually going to be talking about a few more things than just those two. Okay, so I'm going to be showing you all an image or a document that looks like this pretty much in every set of slides that I do. This is from the AP Chemistry course and exam description. Okay, so this is part of a document that College Board has published. You can access these slides and click on this link for yourself if you want to check it out. What this document does is it basically lays out all the things that you need to know for AP Chemistry. Okay, and I'm going to be using this document to plan our journey through AP Chemistry. Okay, this is my first year teaching the course, so I don't really have any experience with this other than when I took the course, but that was several years ago, like 13 years ago, so things have changed since then. So I'm going to be using this document here to sort of guide us through all the content. So, what is the goal or the objective here for this topic? It says the mole allows different units to be compared. Let's actually focus here on this learning objective. It says we're going to learn how to calculate quantities of a substance or its relative number of particles using dimensional analysis and the mole concept. And that is exactly what we're going to be doing today. Okay, I'm going to be going through a few other little things prior to this objective here, but this is the main objective for the day. This stuff over here, the essential knowledge, I'm not going to read that to you because that would take a long time. If you want to read this, it's not a bad idea. This is mainly for me to look at and to understand, what are all the things that sort of go into this learning objective. Okay, so this AP Chemistry course and exam description, not only is it good for students, but it's really good for teachers to help them plan. Okay? All right. Table of contents. So we're going to go through some slides over these 5 things: measurement, significant figures, dimensional analysis, moles, and molar mass. These numbers in brackets are the textbook sections that go along with these slides, okay? And almost always, whenever I have slides, there's going to be a section of your textbook that goes along with that, okay? So this is like Chapter 1, Section 3, Chapter 1, Section 5, etc. Also, I'm going to be publishing a second video which is purely on problem solving. Okay, so this is going to be, this first video here that I'm recording right now is going to be over the slides. Think of it as just like lecture or notes in class. And then problem solving, this is going to be a separate video where I actually record with my document camera. I'll show you that really quickly. Here, let me full webcam. Okay, so this is a document camera. What it does is it allows me to basically record things that I'm writing on my desk or whatever. Okay, so since we don't have a whiteboard, since we're not in school, I can use the document camera to still essentially have a whiteboard and show you guys how to solve problems. Okay, so it's gonna be useful for me to show you guys examples and walk you guys through stuff. Okay. All right, so the problem solving section will be on converting amounts between mass, moles, and particles, which, if we go back, that is exactly what the learning objective is. Okay. All right, so let's dive right in here. So first little thing I need to talk about is units. I know it says measurement, but really I want to talk about units. So anytime you measure something, okay, like if you're a scientist or just a person, you need to measure something with units. Okay, so it says here, scientists use the international system, or the Système International. I don't speak French, so that probably sounded really bad. Or the SI system. Okay, so this is what this is called, the SI system. They use this to keep track of their units used in measurement. This system is based on the metric system, and the United States is one of very few countries that does not use the metric system as their official system of units, which is kind of unfortunate, because what that means is kids like you grow up and you're not naturally used to using metric units, so it can be, or the metric system in general, so it can be kind of confusing for kids, especially like in high school when they first start getting into science, having to like go back and forth between the imperial system, which is kind of what the United States uses, and the metric system, or the SI system. So we're going to have to use the metric system, okay, because as it says here, scientists, including those in the United States, almost universally use the metric system when making measurements and performing calculations. And that is true, okay? So there are some cases where, you know, the imperial system can be useful, or it'll get used, but for the most part, if you're doing anything involving science, you're probably using the metric system, okay? And here are the metric system units. Now there's more units than these, but these are the fundamental units, okay? I'll talk about what that means in just a minute. So we've got these different quantities, these different things that you might want to measure. So for example, you might want to measure the mass of something, how much it weighs. You might want to measure the length of something, time, temperature, electric current, amount of substance. There's our mole. We're going to be talking about that today. And then luminous intensity. Okay, so let me just go right off the bat and tell you that we're probably never going to see this again. Okay, so luminous intensity, the candela, I honestly cannot think of a time, right? And I've been doing science for like 15 years, right? So I can't really think of a time where like I had to care about this very much, all right, other than just like knowing it exists. So yeah, we're obviously going to be spending a lot of time talking about the mole. We're not going to be doing too much with electric current in here, if anything. So this is not something we have to care about too much. Temperature is important. Temperature, you can measure things in Fahrenheit, Celsius, or Kelvin. We'll talk more about temperature and why Kelvin is important later. Okay, and then we get to these three, and these three are big. Mass is important, length, and time. I want to talk a little bit about length. One thing you might not notice on here is like a physical quantity that we measure would be area or volume. Okay, and those two things do exist, right? Like area, you can measure the amount of like land that you own using area, or you could measure the amount of gasoline you're buying in volume, right? Like gallons. But here we only have length, okay? And that's because this is a list of fundamental SI units, okay? All the other units that get used in measurement are built out of these, okay? So for example, area is a length times a length, right? Like if I have a piece of paper here, I'll get a post-it note here. Okay, if I want to know the area of this post-it note, let me get my screen bigger here. I can measure this length and then this length and multiply them together, and that gives me the area, right? So that the unit would be meters squared, right? Because it's meters times a meter. Same thing goes for volume, right? I don't really have a, oh, here we go, I do have something. So I have this almost solved Rubik's Cube. Okay, you can see I've got some of it looking pretty good here. I can never remember how to finish these things. But you could measure the volume of a Rubik's Cube by measuring the length, the width, and the height, or the depth, or whatever, multiplying all three of those together, and you get the volume of the cube. Well, that is just length times length times length, so our unit would be the meter cubed. Okay. Another example, just to help you guys out, speed, okay, or velocity is how fast you're going or how much length you are traversing in a certain amount of time. So like meters per second. Okay. There you go. Okay, so there's tons of different units that you can actually build out of these units. When you get into physics, then you really start getting into like some real crazy combinations of these units. But in chemistry, it's really not that much more complicated than this, right? And we're going to be talking a lot about moles. Okay, so let's move on here. One other thing that we're going to sort of get used to, we're not going to do a whole lot of this like right off the bat, but one thing that I need you to start thinking about and that we're going to be using throughout the course are metric prefixes, okay? And this is really where kids in the United States are kind of like at a disadvantage compared to other kids throughout the world. Because if you grow up in like France or Germany or China or Australia, you would already know some of these things, okay? And these would be like second nature. Like you wouldn't even have to think about it. But for us in the United States, like we don't use these prefixes on a regular basis. Some of them you're going to recognize, but it's just a little bit trickier for us, okay? So let's talk about, let's go back to the last slide. Let's talk about meters. Okay, so meters are the fundamental SI unit for measuring length, okay? Now, if we're measuring something that's, you know, about human size, then we can just measure it in meters, and that's fine, right? That's totally reasonable, right? But if we're measuring something that is enormous, okay, or not even enormous, but just really, really long, then we might not want to use meters, right? Because we might start measuring it, and it might be, you know, thousands and thousands or millions or billions of meters, right? So that's when these prefixes can come in handy. So probably one that you recognize here is kilo, K-I-L-O, okay, with the symbol here, K. A kilometer would be 1,000 meters, all right? So 1 kilometer is 1,000 meters. And this kind of keeps going up the list. There's lots of these prefixes. 1 million meters is a megameter, 1 billion is giga, and 1 trillion is tera. You probably recognize these from talking about computers or your phone, right? Megabytes, gigabytes, terabytes means the same thing. Okay, so a byte is just a B-Y-T-E is a unit that gets it's like a piece of memory in your phone or in a computer, and a kilobyte is 1,000 of those, mega is 1,000,000, etc., etc. Okay, so that's kind of what we use for when things get really big. Now going in the other direction, when things get really small, we have these prefixes, okay? And I'm not super convinced that we're going to be talking about deci very much. I don't use that one very much. The ones in blue, they've highlighted here to tell us that these are like the more common ones, okay? Really, I find that centi gets used a lot, milli gets used a lot, micro and nano, not so much these down here. So these are things that are like really small, okay? So for example, if you're measuring the size of like the length of your finger, okay? Well, it doesn't really help to use meters, right? Because your finger is this big and a meter is like way bigger than that, okay? So, that's not very useful. But if you measure it in centimeters, you could take a ruler or something and you'd find that your finger is probably, less than 10 centimeters, okay, but more than one. So there are so this is kind of tricky how this table works. This means that there is 0.01 meters in a centimeter, okay? It's kind of like the inverse here. So there's 100 centimeters in a meter, okay? So the way that this works, let me just go through this one more time. This number tells us how many meters, or how many of the base unit there are in this prefix. Okay, so let's talk about kilometers again really quick. There are 1,000 meters in a kilometer. Okay, there is 0.01 meters in a centimeter. Okay, so you have to be careful, right? Whenever we think centimeter, we think 100, right? Whenever we think milli, we think like 1,000, right? That's not what that number tells us here. And that's because it works in that specific way, right? This is telling us, this number here, how many of the base unit there are in that prefix. Okay? So just to go way deep on you here, you probably heard of nano, like nanotechnology. Nanotechnology has to do with stuff that's really, really small. So there is 0.000000001 meters in a nanometer, okay, or 10 to the minus 9 meters in a nanometer. Okay. All right, enough about that. When we encounter these metric prefixes, I'll show you how to use them when I am going through examples that involve them. Okay? All right. I'm not going to spend a ton of time talking about significant figures, mostly because I hate them, and secondly, because I think they're not that useful, and I also don't think that they really become super important for like a high school student. I think it is interesting to learn about them and what they mean, but we're not gonna torture ourselves trying to nail everything that there is to know about significant figures. So I'm basically just gonna read a little bit of this and fly right through it. Whenever you take a measurement, only a certain number of the digits in that number are significant. Okay, and this is a good little example. The manager of a shipyard estimates that there are around 9,000 shipping containers located on his property. The mass of one of the containers was measured to be 9,255 pounds, or 9,255 pounds. Okay, so there were two different measurements there. The first one, around 9,000 shipping containers. We would say that this number, or this measurement, has one significant digit, the 9. Okay. Saying that it's around 9,000 means that you don't know, right? Like you didn't actually go through and count. It's not an exact number. You're just sort of guesstimating that there's around this many. So we can only be confident, or we can only really take this first number here, this 9, as being the only sort of significant digit in this number, okay? However, when they measured one of the containers, it was 9,255 pounds. So they put this thing on a scale, and they actually got some more numbers here, right? Enough resolution to actually have 4 digits here, 9255, 9,255. So all 4 of those digits are significant, okay? So that's kind of the concept, all right? Sort of the more resolution you have in your measurement, the better or more significant that measurement is. There are some rules when it comes to counting significant figures. Hopefully you did this last year. If you had me, you definitely did, because you saw these slides. If you had Miss Perkins or Mr. Morgan or Mr. Reed, hopefully you guys went over significant figures. I'm not going to go through all this in detail right now. If you want to read this yourself, it's probably a good idea to review. You can also find, if you read down there at the bottom, it says you can also find an alternative explanation in your book on page 14 and 15. It's just another sort of set of rules that's written a little bit differently in case this doesn't work for you. Okay, and then I've got 2 slides here that go over how to apply significant figures with operations, meaning adding, subtracting, multiplying, and dividing. Okay, and once again, I'm not going to go through this right now. In the homework, there are a couple of problems that ask you to work with significant figures. You will need to refer to these rules or look in the book for the examples to help you solve those problems if you don't know how to do them. Okay, dimensional analysis. By the way, guys, feel free, since this is just a video, right? If you are finding yourself like needing a little bit of a break, just hit the pause button, go get up, stretch, grab a drink of water, whatever. You know, I'm recording this all in one go, right? But that doesn't mean you have to watch it all in one go. So feel free to pause and get up and go do something if you're finding yourself having difficulty concentrating or whatever. You know, you're not going to hurt my feelings. Okay, so dimensional analysis. This is also referred to as like unit conversion, or I think they call it here the unit factor method. Basically, it says it is often necessary to convert a given result from one system of units to another. For example, converting from like the imperial or English system to metric. The best way to do this is by using dimensional analysis. Okay, that's what I refer to this as, dimensional analysis. You can find a ton of examples of dimensional analysis in your book, starting on page 18 and actually like all through the book. And I'm going to work through several examples of this. It says at the end of the video, listen, it's going to be in the second video. Okay, so like the problem solving video, I'm going to go through a lot of examples of dimensional analysis for you. Okay, now we have gotten to the good stuff here, moles. All right, so if you don't remember talking about moles last year, or even if you do, I guarantee you probably need a refresher. Okay, because I can remember learning about moles in high school and still not really getting it all that well until like after high school was over. Okay, so it's my goal here to help you understand moles better than I did when I was in high school. So let's go through this. It says when you measure an amount of substance. Okay, so let's say you've got a little handful of something in your hand. Okay, when you measure amounts of a substance, you have three options. Number one, you can measure the mass in grams of the substance, like how much does it weigh. That's one method. You could count the number of individual particles in that substance, okay, like the individual atoms or molecules. That's not really possible, okay, so atoms and molecules are so small, we're going to talk about that in a few minutes, you can't really get down and like count them individually, certainly not by yourself, and not even really with the use of the most powerful technology that we have. Okay, so you can measure the mass of something, that's doable using a scale. You can't really count the number of things by yourself. The third way that you can measure something is by counting the number of sets of particles. Okay, and we're going to talk about that. Sets, what does that mean? So sets, question mark. And if you had me last year, you should remember me talking about this concept of a dozen. Okay, so like what does this mean? So a dozen. Well, you guys know what a dozen is, right? 1 dozen is 12 of whatever you're talking about, right? So you could have like a dozen eggs that you buy at the store, or a dozen donuts that you buy at Krispy Kreme. 1 dozen is equal to 12, right? Of whatever it is you're talking about. That's what I mean by sets, okay? So you can count the number of sets. Now that's still not really easy, okay? Because if you can't count the individual particles, then how can you tell if you're counting the right number when you're doing your sets? So in chemistry, there's a little bit of trickiness that we have that goes on here, okay? And I'm going to get to that here in just a couple of slides. But for now, here's what I need you guys to know. Our sets are not going to be dozens, okay? Our set is a mole, okay? And that's what a mole is. It's a number. It's a set, right? If a dozen is 12, right? That's an easy number to think about. A mole is 6.022 times 10 to the 23rd, which is a massive number. The next slide is going to talk about this, okay? But that's the magnitude that we're dealing with here in chemistry. Because atoms and molecules are so small, our sets are huge, okay? They're gigantic, all right? So let's actually talk about how big of a number that is. First of all, it's pretty much close to impossible to imagine just how big a number this is. So, I mean, here's the number written out, right? 6.022 times 10 to the 23rd. It is a very large number, right? This would be like 1,000, a million, billion, trillion, quadrillion, quintillion, sextillion. So it's 602 sextillion, okay? The human brain has trouble, like imagining millions of things, right? Let alone billions of things. So like this number is just like astronomical compared to that. There's a couple of interesting little tidbits here. 1 mole of seconds, okay, so if you had a dozen seconds, that'd be 12 seconds. That's easy, right? But if you had a mole of seconds, that's this many seconds, right? 6.022 times 10 to the 23rd. That is over 4 million times the age of the Earth, okay, and the Earth is several billion years old, all right? So that's over 4 million times 4 billion. Like it's a crazy amount of time, right? So a mole of just 1 mole of seconds is longer than you can really fathom, right? Because it's already crazy to think about the age of the Earth. Well, 4 million times that is even crazier. Here's another one. Okay, 1 mole of marbles, 6.022 times 10 to the 23rd marbles. That is enough marbles to cover the Earth in 50 miles of marbles. Okay, so just imagine like looking at the Earth from like outer space, covered in 50 miles of marbles all around, right? Including like the oceans and stuff, right? That's a lot of marbles, right? 12 marbles, a dozen marbles fits in your hand. A mole of marbles covers the entire Earth in 50 miles of marbles, right? So that's crazy. All right, well, here is the important part of this slide, okay? And I've bolded it here because it is important. 1 mole of carbon-12, okay, which is an element, it's a specific isotope of an element. 1 mole of carbon-12 is 6.022 times 10 to the 23rd atoms of carbon-12. That is 12 grams of carbon-12, okay? So this is actually the definition of 1 mole. This is what a mole really is, okay? Not only is it 6.022 times 10 to the 23rd atoms of carbon, but it's also 12 grams of this type of carbon, okay? That's going to be important here in just a minute. But before we get into the nitty-gritty details of that, just think about how small an atom has to be in order for that many to fit into just 12 grams. Okay, so like I've got my phone here. Okay, my phone weighs more than 12 grams. Okay, so like if this was made of carbon, this would be way more than 1 mole of carbon. Okay, like this phone probably weighs like hundreds of grams. All right, so 12 grams of carbon, very small amount. Like you could easily fit that in the palm of your hand. You've got this many atoms of carbon in there. Okay, so just think about how small those atoms have to be in order to pack that many of them into such a small amount of space, right? Pretty small. Okay, so that's the type of thing that we deal with in chemistry, right? Like what is the universe made of? It's made of atoms. That's how small they are, right? Okay. Last thing for this video. Like I said, I know this is a long one. It's like 28 minutes. Hoping that the ones so far, 28 minutes so far. I hope that the ones in the future are not this long, but it is what it is, right? Okay. All right, so it says here, we just discovered that the definition of 1 mole is related to carbon. 1 mole of carbon-12 is 6.022 times 10 to the 23rd atoms of carbon-12, which is 12 grams of carbon, okay? So let's actually take out this middle part, okay? Because if these three are all equal to each other, let's just take out this middle part and see what we're left with. It says here, 1 mole of carbon-12 is 12 grams of carbon. Okay, so what I actually want to do, let's back up a little bit. Remember when we were talking about how you can measure the amounts of a substance, right? You have these three options. You can measure the mass, you can count the individual particles, or you can count the sets, okay? Well, the easiest one on here is just to measure the mass, right? If you put something on a scale, you can figure out how much it weighs, right? These two other things were really hard, right? Well, if I can measure how much carbon I have, I can use this right here, this little rule, right? 1 mole is equal to 12 grams. I can use that to figure out how many sets I have or how many moles I have, right? So you can kind of, as long as you can measure the mass of something, and as long as you can figure out what this molar mass thing is, then you can bounce back and forth between these two, okay? And so that's what a molar mass is, okay? This little rule here, it tells us how much 1 mole of a substance weighs, okay? Molar masses are in units of grams per mole, okay? So 1 mole of this weighs X many grams, right? So yeah, here you go. Molar mass of carbon-12 is 12 grams per mole. You can find molar masses for the elements which make up the universe on the periodic table, okay? So your all's periodic table looks a little bit different than this. I'll try to use yours from now on. I just have this picture ready to go. By the way, you can also find in your book, you can find periodic table in the back cover. Sometimes when you're reading the book, it'll say front cover, but it's actually in the back cover. I also included, as you guys know at this point, a laminated and just regular paper copy of the AP periodic table in your all's materials that you picked up at school. Anyways, doesn't matter. These numbers here at the bottom of each entry on the periodic table are the molar or atomic masses for that element. Molar mass and atomic mass kind of mean the same thing if you're just talking about an element, okay? So we're going to talk about why these numbers aren't whole numbers very soon, like next week or the week after, because you know, if I jump back here, right, it said that the molar mass of carbon-12 is exactly 12, but here it says 12.01. We're going to talk about why that is. Some of you may remember why that is from last year, talking about isotopes. Okay, and I believe this is the last slide. Hooray! You can so you can just look up the molar masses for elements in the periodic table. You don't have to calculate them; they're just there. Okay. If you have a compound, some sort of more complicated chemical, you can calculate it just by adding the numbers up. Okay. So it says here methane. This is one of my favorite examples. This is 1 carbon and 4 hydrogens. You can just add up the molar mass for 1 carbon plus 4 hydrogens to get the molar mass for this overall chemical, right? So carbon is 12.01. I'm getting this from your periodic table. Okay, so 1 times 12.01, that's for carbon, plus 4 times 1.008, that's for hydrogen. This is equal to 16.04, okay? And actually, if you put that in your calculator, that's not exactly what you get, but that's due to some significant figure rules there. So anyways, the molar mass for methane is 16.04 grams per mole, right? So if you had some methane and you measured its mass and you found out that you had exactly 16.04 grams, you would know that you had 1 mole of methane. Okay, which means that you have 6.022 times 10 to the 23rd molecules of methane. Okay, so we're going to be using all this information later on in the semester. All we really need to do today, which is what I'm going to do here in the next video, is learn how to do these conversions. Okay, between mass, moles, and number of particles. Okay, so that's what the next video is going to include. All right, let me zoom back out here. All right, so if you watched that all in one sitting, bravo, congratulations. If you did not, then I think that's probably smarter. Remember, like we talked on Wednesday, the goal is for you to watch these videos prior to us having class. Okay, this whole concept is kind of like a flipped classroom. That is what the concept is called, watching the instruction prior to meeting in class. What this is going to do, right, if you can get into the habit of watching these videos, even if you're not like working on your assignments ahead of time, or even if you don't necessarily understand everything that I talk about during the video, what this does is it enables you to show up to the Zoom meeting and we can just talk about it, right? So if you show up to the Zoom meeting and you haven't watched the video, then all the conversations that I'm having with other kids are gonna seem like really over your head, and you're probably just gonna want to go watch the video then anyways, right? So I'm gonna do my best to make sure that these videos are up ahead of time. Like, I'm gonna shoot for like 2 full days ahead of time, and that means that you'll have like 48 hours in which you could watch the video. Okay, and like I said, hopefully they're going to be shorter than 35 minutes. All right. Okay, well, that's it for today. Thanks for watching.